So in the previous section, we learned about the rate laws, and if the concentration of something was doubled, what would happen to the rate of the reaction, and how to find the reaction order with respect to different reactants. This is incredibly useful. But unfortunately, what this doesn't do is it doesn't allow us to predict anything about how much of a reactant or a product will be left after a specific time based on a certain rate law. So that's where the integrated rate law comes in. And it turns out that there are three different integrated rate laws. There's one for the zero order reaction, okay, one for the first order reaction, and one for the second order reaction. Before we talk about the specific integrated rate laws, I want to look at some of the variables, and I'm going to use the zero order to do that. The concentration of A at some t is the concentration of A after some time. K is the rate constant. T is the time, usually in seconds in the examples presented here. And A0 is the initial concentration of A. In the case of the first order, it's the ln of the concentration of A at some time and the ln of the initial concentration. And in the case of the second order, it's 1 over the concentration of A at some time and 1 over the concentration of A0. You'll also notice here that these are both negative K and this one is positive K. So that's basically that. One way that this can be used experimentally is to graph the concentration, the ln of the concentration, and 1 over the concentration versus time. And in this case, if you graph the concentration versus time and you get a straight line, if it's a zero order reaction, you will find that the slope of that line is negative K. All right. Why is this? Because y equals mx plus b. Y is the concentration of A as time goes on. X is time. M, the slope, is negative K. And B is just A0. If you graph the ln of the slope versus time and you find that you get a straight line, then you know that it's a first order reaction with respect to that reactant. Here we have y is the ln of A at some time, and x is time. Again, if you get a straight line, the slope is negative K. In the case of a second order reaction, we have to graph 1 over the concentration versus time. And notice here that this case is negative slope. Here's a negative slope. This one has a positive slope because it's positive K is the slope. The x values again are time. And the b is 1 over A0. So you can see that this could be incredibly useful. And I'll show an example of this in a minute. The other thing you can do is the half-life, the T1 half. And for a zero order reaction, it's a concentration of A0 over 2K. For a first order reaction, it's 0.693 over K. And for a second order reaction, it's 1 over KA0. If you notice here, both the zero order and the second order reaction, the half-life depends on how much you started with. But for a first order reaction, the half-life does not depend on the amount that you started with, which makes the half-life of a first order reaction very useful. So these are some information that you can find based on the integrated rate laws. Very much like the rate laws themselves, it can be better to demonstrate this by examples than by a lecture slide. But before we do that, I do want to show that you can derive this first order half-life reaction where you essentially are setting the ratio of AT to A0 to 1 over 2. And this is how that is derived. You could also derive it for the other ones, but I'm not going to go through this here. Here we're looking at some concentration data and some time data that maybe was collected in a lab. And if we look here, okay, we have the concentration of A as time goes on. I can tell this is the concentration of A because it started at 0.62 molar and it ended up at 0.024 molar, meaning that we know A is being used up, or the concentration of whatever we're measuring here is being used up, and therefore it's A. The blue values are calculated. I can easily determine the ln of this concentration in Excel, just equals ln of this cell and drag it down. And I can easily determine 1 over the concentration by taking this cell, 1 divided by this cell, and drag it down. So I could find the ln of the concentration and the 1 over the concentration in a few seconds. And basically, I end up with this concentration, ln of concentration, and 1 over concentration data. Well, what can I do with this data if I want to know what the reaction order is with respect to A? The answer is I can plot it. Okay? And if I plot the 0 order test, I have the concentration of A versus time, and this clearly is not a straight line. If we look at the r squared here, which for a straight line would be 1, you can see that it's not even close, okay, just by looking at it. But the r squared is 0.86, which is not even close to 1. So we know this isn't 0 order. Let's look at the first order. In the first order case, we put ln of the concentration on y and time still on the x. And here you can see we have a nice straight line with an r squared very close to 1. Not only does that tell me that the rate equals k concentration of A to the 1 power, or just rate equals k concentration of A, it also tells me the value of k, because k is the negative slope. So in this case, the k is 0.0279. All right, so that is basically what this tells us. Just to prove that it's not a second order reaction, I put 1 over the concentration versus time, and I graphed that. Again, all of this data came from these tables, so now I'm graphing this time versus this 1 over concentration. And in this case, I find that it's not a second order reaction because the r squared isn't close to 1, or this clearly is not a line, right? It's a curve. So if we graph these things, we can actually find reaction orders, and more than reaction orders, we can actually find the rate constant as well. This can be incredibly useful. Now let's look at a few examples where we're going to mathematically do this, right? You wouldn't be asked on a test to make this graph, although we do exactly this in the lab. So let's look at this example, and we're actually going to do 3 examples. And like usual, I'm going to switch over to the camera so I can write. So the first thing says, consider the following reaction. A plot of ln of x versus time gives a straight line with a slope of negative 8.21 times 10 to the minus 2 per second. Assume the reaction only starts with x. So we have x in the gas phase yields y in the gas phase plus z in the gas phase. And it says, what is the rate constant for this reaction? Well, we know that it's a first order reaction because if we graph ln of x versus time, which is just what we talked about a second ago, we get a straight line, and we know the slope of that straight line. So if we know the slope of the line, we also know the value of the rate constant. The slope is the negative rate constant, so the rate constant is positive 8.21 times 10 to the minus 2 per second. Now that I know this, I can write the rate constant expression. And there's basically 2 ways to do this. Since I know it's first order, rate equals k, concentration of x to the 1. Or if you prefer, you could write it as rate equals 8.21 times 10 to the minus 2 per second x, because we know k, all right? So whether you put it this way or you put it this way, I think it's arguable. It depends on what the question is asking. I'd probably write it this way, but I don't think this is wrong as well. The next thing is, what is the half-life of the reaction? Well, you're going to have to use the lecture slides in order to know the expressions for the different half-lives. All right, you also need to know the integrated rate laws. So basically, you can look it up right here on this slide. So if we look for a first-order reaction, the T1 half equals 0.693 divided by K, which in this case is 0.693 divided by 8.21 times 10 to the minus 2 per second. And when you do that math, you find that the half-life of this reaction is 8.44 seconds. That means that half of x will be gone in 8.44 seconds. This is a pretty fast reaction. In another 8.44 seconds, another half will be gone. So essentially you go from 50% to 25%, and then in another 8.4 seconds, you lose another half. That is what the half-life means. But we can calculate it in this way. Note that it is very much dependent on the order of the reaction. So we need to get the right equation from the previous slide, as I showed you. The next question says, if the reaction starts with a concentration of x of 0.1 molar, what is the concentration of x after 1 minute? So one thing that we need to be aware of here is that 1 minute is 60 seconds. Don't forget that our rate constant is per second, not per minute. Usually we use seconds here instead of minutes, okay? So basically we just need to make sure that the units of time match. So this is going to be 60 seconds. Well, now, again from the previous slides, I want to use the integrated rate law for this, which is the ln of a, sorry, I should put it back on the video here. Okay. The ln of a at some time equals negative kt plus the ln of the initial concentration. I guess it should be of x. All right, because we're talking about a specific reaction, not the A reaction. We're talking about X. All right, so this is our integrated rate law. Well, we know the initial concentration of A. We know K, which is, sorry, it's not all on one screen, which is not helpful. We know K, and we know T, 60 seconds, and we know the initial concentration. What we don't know is this. So let's plug in what we know. The ln of the concentration of X at some time is equal to negative K 8.21 times 10 to the minus 2 per second times T, which is 60 seconds, plus the ln of the initial concentration of A, which is 0.001 or 0.100, and I'm going to leave the molar off there. All right. So simplifying this, I multiply these two numbers and I take the ln of this number, and I get the ln of X at some time is equal to negative 4.926 plus 2.303. All right. Now I want to add these two numbers together, and I'm going to find that the ln of X at some time is equal to negative, sorry, this is negative. It's negative 4.926 plus negative 2.303, and I'm going to get negative 7.229. All right. How do I get rid of the ln? I do on my calculator, the shift ln, or the opposite of the ln, which is e to the power. So I want to take e to the ln of xt, which is just the concentration. I'm going to go over here now. Concentration of X at some time is equal to e to the negative 7.29, which is 7.26 times 10 to the minus 4 molar. All right, so we know the concentration of X after some time. It now asks us, what are the concentrations of Y and Z after 1 minute? Well, if all of the X turned into Y and Z, I'd have 0.1 molar Y and 0.1 molar Z. But in this case, not all of it turned, because a little bit of it is still X. So it's 0.100 molar minus the part that's still X, which is 7.26 times 10 to the minus 4 molar, which is equal to 0.0993 molar. All right, since there's a little bit of X left after the 1 minute, not all of it has been turned into Y and Z. All right, let's look at another example where we go through similar type of problem, but we're looking for some different variables. In this case, we have years as the amount of time instead of minutes. It says a slow environmental reaction has a half-life independent of the initial concentration. So it's a first order reaction. And the half-life is 455 years. It says, how long will it take for 22.3% of the sample to react? It turns out, okay, that it is easier, sorry, this shouldn't be here, okay? It turns out that it's easier for us to use K than to use the half-life. So if it says how long will it take for 50% of the sample to react, the answer would be 455 years. All right. Or if it's how long will it take for 75% of the of it to react. It's again an even number for half-lives. So it'd be 455 plus 455 years, which is what, 910 years. All right. But in this case, it's 23.3% of the sample. This is not going to be easy to figure out because it's not an even number of half-lives. Said another way, we're much better off using K. So if you'll remember, for a first order reaction, T1 half equals 0.693 over K. All right. So it's going to be 0.693 divided by our, sorry, what am I doing? All right. It's going to be 455 years equals 0.693 divided by K. Cross multiply by K, divide by 455 years, and you're going to find that K is equal to 1.52 times 10 to the minus 3 per year. All right, so I just cross multiplied by K, so I got 455K equals 0.693, then divide by 455, so it's 0.693 divided by 455, and I found K. Now I can use the integrated first order rate law, which is the ln of the concentration of A at some time is equal to negative KT plus the ln of concentration of A initially. Okay, so we are going to assume that the initial concentration of A is 1. Because why not? It's the easiest number to assume that it is. Okay, but it doesn't really matter. If the initial concentration is 1 and it went down by 22.3%, then what's left, so this is concentration of A, 0. The concentration of A at some time is 0.777. All right, 1 minus 0.223, which is what I just crossed out here. So 1 minus 0.223, which is 0.777. Now we can just plug in. We know everything. Okay, we know the concentration of A at some time, it's this. We know the initial concentration of A, we made it up, it's 1. We know K, because we just found it. Now we can find T. So the ln of the concentration of A0, 0.777, equals negative K, 1.52 times 10 to the minus 3 per year, plus ln, times T plus ln of the initial concentration of A, which is 1. Okay. The ln of 1 is 0, so I can get rid of that. The ln of 0.777 is negative 0.252 equals negative 1.52 times 10 to the minus 3 per year times T. Divide by negative 1.52 times 10 to the minus 3 into this one, and what you find is T equals 166 years. Okay, which makes sense, right? It's roughly half of this, and we're going roughly half of a half-life, but not exactly half of a half-life, so this is the easier way to do it. All right, next question. It says, if there were initially 2.30 times 10 to the 18 molecules of reactant, how many molecules will remain after 9,980 years? Well, it turns out we're going to use the exact same equation to do this one as we did before. Okay, the difference is we have a different amount of time and we have a different variable. So in this case, we're going to use the exact same equation. The ln of the concentration of A at some T, which is what we don't know, and instead of concentration this time, we're going to give molecules this time, which is the same. Okay, they're related to each other as long as the volume doesn't change, which we assume that it doesn't. K is still the same K, negative 1.52 times 10 to the minus 3 per year. In this case, the time is 9,980 years plus the ln of 2.30 times 10 to the 18 molecules. Because we started with that number of molecules. And I'm going to leave off molecules just so I don't have the units following me around here. All right. Now, let's do the math. So, the ln of the concentration of A at some time is equal to, multiply this times this, and I get negative 15.17 plus, when I take the ln of this, I get 42.28. Add those together. The ln of the concentration of A at some time is equal to 27.11. Take the inverse of the ln, or e to this power. E to the ln is the concentration of A at some time. E to the 27.11 is 5.94 times 10 to the 11 molecules. All right, so half the battle here is just doing the math. The other half of the battle is making sure we're using the proper equations. So there's a different integrated rate law for a first order reaction as opposed to a second order reaction as opposed to a zero order reaction. To put that into perspective, let's look at an example that's not a first order reaction. So it says, consider the following reaction. A plot of 1 over x versus time gives a line with a slope of 5.8 times 10 to the minus 2 per molar second. And then we have this reaction here. What is the rate constant for this particular reaction? Well, in this case, it's 1 over the concentration of reactant versus time gives us a straight line, which tells us that this is a second order reaction. In a case of a second order reaction, the slope is the reaction order, is the rate constant, sorry. So it is 5.80 times 10 to the minus 2 per molar second. What is the rate constant expression? The rate constant expression for the reaction. Rate equals K, concentration of X, squared. We know it's second order because 1 over X versus T gives us that straight line. What is the half-life for this reaction? Again, we go back to the slide and we need to find the half-life. So in this case, we're given the initial concentration, which is important because the half-life of a second order reaction and a zero order reaction depend on the initial concentration. For a second order reaction, when we look on the slide, we find that T1 half equals 1 over K, concentration of A initially, which equals 1 over K, 5.80 times 10 to the minus 2 per molar second, times the initial concentration, 0.100 molar. And when we do all that math, we find that the half-life of this reaction is 172 seconds. Another question is, if the reaction starts with concentration X of 0.25 molar, what is the concentration of X after 185 seconds? So the integrated rate law is very good for this, but don't forget we need to use the correct integrated rate law. So since this is a second order reaction, we have to use the second order integrated rate law. That is the 1 over the concentration of X at some time equals KT plus 1 over the initial concentration of X. Okay, in this case, we know the initial concentration of X, we know K, and we're given the time, 185 seconds. So 1 over the concentration of X at some time equals K, 5.8 times 10 to the minus 2 per molar second, times T, which is 185 seconds, plus 1 over the initial concentration, 0.250 molar. We find that 1 over the concentration of X at some time, I'm just going to clean up all these numbers, multiply these two together, and then add this one in, is going to be equal to 14.72 per molar. To solve this one, I take the reciprocal of both sides. So I take 1 over 14.72, and I find that the concentration of X at some time is equal to 0.250 0.0679 molar after the 185 seconds. So I simply took the reciprocal of this value. Finally, it says, what is the concentration of U after the 185 seconds? So in this case, every X yields a U. Said another way, if the reaction proceeded completely, the concentration of U would be 0.25 molar because all X becomes U. Well, it didn't go completely. It started at 0.25, but there's still some X left. So if I take 0.250 molar and I subtract the X that's left, is 0.0679 molar. And again, this works because we have a one-to-one stoichiometry. I find that there's 0.182 molar U that is found in solution after the 185 seconds. So these problems are challenging. All kinetics problems really are challenging, and they take practice. So it's going to be really important that you practice with these on your own, because if you get stuck somewhere, it's better to get stuck somewhere, when you're not taking the test.